Dear students, in this video we are going to study about the basic properties of magnets, magnetic dipole moment, magnetic field, properties of magnet, magnetic field lines, magnetic flux, uniform and non-uniform magnetic field. About the basic properties of magnets. First one being magnetic dipole moment. Let us consider a bar magnet as shown in this diagram. Let Qm be the pole strength of the magnetic pole and L be the distance between the geometric center of bar magnet O and one end of the pole. The magnetic dipole moment is defined as the product of its pole strength and magnetic length. It is a vector quantity denoted by a letter Pm. Now, this is a bar magnet having two poles, south pole and the north pole. These two poles are separated by a distance of 2L, that is called as the magnetic length. And now the dipole moment is given by Pm equal to Qm into D. So D is the vector drawn from south pole to north pole and its magnitude is given by D equal to 2L. The magnitude of magnetic dipole moment is given by Pm equal to 2qml. The SI unit of magnetic moment is given by ampere meter square. The direction of the magnetic moment is from south pole to north pole. Next is the magnetic field. What is a magnetic field? The magnetic field is the region or space around every magnet within which its influence will be felt by keeping another magnet in that region. And how to define the magnetic field? It is denoted by letter B. The magnetic field at a point is defined as a force experienced by the bar magnet of unit pole strength. And that is given by the expression B equal to 1 by Qm F, and its unit is given by Na power minus 1 m power minus 1. N is Newton, A is ampere, and m is meter. What are the types of magnets? Usually the magnets are classified into natural and artificial magnets. The examples for natural magnets are iron, cobalt, nickel, etc. The strengths of natural magnets are very weak and the shapes of the magnet are irregular, whereas artificial magnets are made in order to have desired shape and strength. And if the magnet is in the form of a rectangular shape or cylindrical shape, then it is known as a bar magnet, like this. Now let us study about the properties of magnets. The first one is the freely suspended bar magnet will always point along the north-south direction. Second, the magnet attracts or repels another magnet or magnetic substance towards itself. The attractive or repulsive force is maximum near the end of the bar magnet. And when a bar magnet is dipped into iron filings, they cling to the ends of the magnet, showing that the power of magnet will be maximum at the poles. When a magnet is broken into two pieces, what will happen? Each piece will behave like a magnet with two poles, their ends. And the two poles of a magnet have a pole strength equal to one another. The length of the bar magnet is called the geometrical length, whereas the length between the two magnetic poles in a bar magnet is called its magnetic length. Magnetic length will be always slightly smaller than the geometrical length. What will be the ratio of the magnetic length and the geometrical length? That's given by 5 by 6. It means magnetic length by geometric length will be equal to 5 by 6. It is equal to 0.855. So this diagram shows the property of a magnet when it is suspended freely. That will show the northerly direction. And here the ends of the bar magnet will have more attractive power. And this is the diagram showing the magnetic lines of force drawn by using a compass box. And in this diagram, the bar magnet having geometrical length which is equal to L, whereas the magnetic length of a bar magnet will be equal to 2F. That's the distance between the two poles of the magnet. And when you break apart the bar magnet, each piece will have two poles like this. Next, we are going to study about the magnetic field lines. What are magnetic field lines? They are continuous closed curves. The direction of magnetic field lines is from north pole to south pole outside the magnet, and from south pole to north pole inside the magnet. The direction of magnetic field at any point on the curve is shown by drawing a tangent to the magnetic field lines at that point. Magnetic field lines never intersect with each other. If they are intersecting, that means the magnetic compass needle would point towards the two different directions, which is impossible. The degree of closeness of the field lines determines the relative strength of the magnetic field. The magnetic field is strong where magnetic field lines curve, and weak where the magnetic field lines are well separated. Next one is the magnetic flux. How will you define the magnetic flux? That is, the number of magnetic field lines crossing any area normally is defined as magnetic flux phi b through the area. Mathematically, the magnetic flux is expressed as b dot a, that's given by ba cos theta, or b cos a. Here theta is the angle between the magnetic field and the area of cross section of the coil. Then we will consider the special cases here when the magnetic field is normal to the surface. That means theta equal to 0. Therefore, the magnetic flux phi b will be equal to Ba. That's maximum. Flux will be there. And when magnetic field is parallel to the surface of the coil, then theta will be equal to 90 degrees. That means the magnetic flux is 0. Suppose the magnetic field is not uniform over the surface, then the equation 3.6 can be written as phi b equal to integral phi dot dA. Magnetic flux will be always a scalar quantity, and the SI unit for magnetic flux is Weber, which is denoted by letter Wb. The dimensional formula for magnetic flux is m squared t power minus 2 a power minus 1. What's the CGS unit for magnetic flux? It is Maxwell. And the relation between Weber and Maxwell is given by this. 1 Weber equal to 10 power 8 Maxwell. How to define magnetic flux density? So the magnetic flux density is defined as the number of magnetic field lines crossing per unit area kept normal to the direction of lines of force. What's the unit for this magnetic flux density? That is given by Weber per meter square or Tesla. Then we will consider uniform and non-uniform magnetic fields. If the magnetic field is said to be uniform if it has same magnitude and direction like this at all the points in a given region. For example, the S magnetic field will be uniform locally, that is at any place. The magnetic field of Earth has the same value over the entire area of your scope. Now, what is non-uniform magnetic field? The magnetic field is said to be non-uniform if the magnitude or direction or both vary at different points in a region, like this. If a magnetic field of a given bar magnet would be like this. So here is a bar magnet, and when you draw the magnetic field lines, it will be like this.